Good morning everyone. Welcome for this course on 1 and 2 dimensional NMR spectroscopy, concepts and spectral analysis. I am Professor Surya Prakash. I served at Indian Institute of Science for nearly 44 years and superannuated as a professor and chairman 2 years back. Currently, I am holding CSIR Emeritus Scientist at SSU. Now, let us start by asking in this course what I am going to offer for you. What is that you are going to learn in this course? First, we will discuss NMR concepts, right from little bit of introduction to spin physics, interaction of magnetic moment with the external magnetic field, how do we get the resonance and what are the interaction parameters, etc. Basic concepts including selection rules we will discuss. Subsequently, we discuss more about the interaction parameters such as chemical shift and scalar couplings. After introduction of these two parameters and discussion extensively on these two parameters, afterwards we will analyze one dimensional NMR spectra where I am going to take n number of examples, lot of examples to make you feel more comfortable. As we go along, I will discuss spin echoes, attached proton test, inept, depth, etc., where we will try to enhance the signal intensity by polarization transfer in inept and depth. Subsequently, I would like to analyze spectra of large number of nuclei, spin half nuclei especially like carbon 13, fluorine, phosphorus, lithium, boron, silicon, nitrogen 15, etc. All those things we will try to analyze several one or two examples for each of these nuclei. And we also discussed relaxation, nuclear over-Raster effect. Then I will introduce concepts of 2-dimensional NMR and what is a 2D pulse sequence, especially pulse sequences involved in COSY, TOCSY, HSQC, DOSY, HMBC, etc. And we will analyze lots of 2D spectra. Numerous examples of 2D spectra would be analyzed like COSY, TOCSY, HSQC, HMBC, inadequate spectra, everything. And finally, we will try to see how we can combine all these 1 and 2 dimensional techniques to analyze the spectrum of any given molecule and how do we assign the peaks and get the structure. This is basically you would like to arrive at by the end of this course. I hope by the end of this course, if you attend all the classes, you would become more comfortable in analyzing the spectra of varieties of nuclei. And by the by, part of it was discussed in the previous two courses also, but in this course more focus is given for understanding the concepts and the analysis of the spectra. With this, let us go further. And for this course I have taken some references. These are the references like High Resolution NMR Technique book in Organic Chemistry by Claridge and NMR Data Interpretation explained by Neil Jacobson, NMR Spectroscopy explained again by Neil Jacobson, and Multidimensional NMR Method for Solution State, which was edited by Gareth Morris and J.W. Emsley, and we have book on organic structure from 2D NMR spectra by Leslie Field and others, spin dynamic by Malcolm Levitt, and number of public domain resources are also there. So I would like to mention at this stage, the materials taken from the books are used only for teaching purpose and not for any commercial purpose. So lot of books have been referred, lot of spectra and information and the material that is required to be discussed have been taken from large number of books. But I would like to stress again, it is only for teaching this course. So no part of this will be copied and displayed to or distributed to anybody. Okay, let us start with the fundamental thing, what an NMR will do. Of course, NMR is an ubiquitous technique. You can see this NMR spectroscopy applied in various branches of science, starting from physics, soil science, agriculture, medicine, hospitals, functional imaging, in unconventional applications like airport for detection of explosives, well logging. You can study NMR microscopy, food technology, structural biology, material science, lot of areas. These areas which I have mentioned are only the tip of an iceberg. Nowadays, you can see almost the utility of NMR spectroscopy in every branch of science, even in engineering applications. So, it is a very, very powerful and a ubiquitous technique. Now, when I say it is a ubiquitous technique, we can ask a question, what makes NMR a ubiquitous technique? What is that which makes it so powerful? First of all, it is a non-invasive or non-destructive technique, and you can study very weak interactions surrounding the nucleus. Microscopic interaction or perturbations that is going on at the site of the nucleus would be studied. And if you go to the periodic table, at least one isotope of every element of the periodic table is NMR active and can be individually studied. And it is possible to study varieties of chemical, biological molecules and even materials. It is possible to obtain the structural, conformational information in all the three phases of matter. Like you can study NMR in solution state, solid state and also in gaseous state, but mostly NMR is practiced in solution and solid state. The dynamics of the molecules or different time scales ranging from picoseconds to microseconds or to seconds can be investigated. So, with this, of course, there are lots of applications, and basically this is the application oriented course where we analyze lot of spectra. We can ask the question, what NMR can do for chemists, pharmacists or biologists who basically want to utilize NMR spectroscopy for their analysis. Of course, it is used for structural elucidation. You can get the structure of natural products and synthetic products which are synthesized in the laboratory. You can study dynamic processes, like you can study reaction kinetics, study of chemical and structural equilibrium is possible. You can study biomolecular structure determination, like structure of proteins, nucleic acids, polysaccharides and varieties of things can be studied. You can use it for drug design. You can investigate structure activity relationships. It is also applied in medicine, used in medicine, especially MRI, magnetic resonance imaging, where you can study metabolomics also, where we can investigate biofluids, cells and tissues. With this basic introduction about the utility of NMR in diverse aspects, diverse areas of science, let us start asking the question, where does this NMR spectroscopy appear in the electromagnetic spectrum? Because it is a molecular spectroscopy. You all know in the molecular spectroscopy there are varieties of spectroscopy techniques like IR, Raman, UV, X-ray, varieties of things. Right from X-ray region to RF region, lots of spectroscopic techniques are available. Now the question is, where does NMR spectroscopy appear in this electromagnetic spectrum? If we look at this electromagnetic spectrum, starting from the gamma ray X-ray, right from right end to left end if I come, you can see there is a radio frequency region. This is where in this region NMR spectroscopy is practiced. If you want to study NMR spectroscopy, you will be in the electromagnetic region of the RF region of the electromagnetic spectrum. conceptual understanding of NMR. Let us go and try to understand some concepts of NMR spectroscopy. First of all, once I say NMR spectroscopy, you cannot avoid discussing spin of the nucleus. If you understand quantum mechanics, you already may be knowing there is spin angular momentum of some subatomic molecules like protons, neutrons, electrons. They have spin angular momentum. For example, proton has positive charge, spin is half, neutron is charge 0, spin half, electron is negative charge with spin half. These are all individual particles have their own spin. Now, what is a spin? Can we try to understand this? But remember, spin is a quantum mechanical concept. There is no good classical analogy at all. You cannot question what is this? What is a spin? How do you explain that? It is not possible. Of course, we will discuss about rotation of the particles, spinning particle rotating about its own axis, etc. But it's all okay to some extent. But actually, it is not produced by the rotation of the particle. It is an intrinsic property of the particle. It is always there even at 0 K, 0 degrees. Then why it is called a spin is the next question. Because it is described with the equations governing the angular momentum P and its vector. And it is a vector. Spin is a vector. Okay, angular momentum is a vector. Now, if you go to the spin of a nucleus, the spins of the individual protons and neutrons, what I said have spin half. Inside the nucleus, we have nucleons. In a word which gives nucleons means combination of neutrons and protons together called nucleons. Inside the nucleus, we have neutrons and protons. These individual protons and neutrons, they combine to give an overall spin for the nucleus of any isotope of an element. How do they combine everything? It was all discussed in one of my previous courses of the NPTEL. One can refer to that. I do not want to go to the more details of that, but it is possible to get the nucleus spin. But then the question comes, do nuclei of all elements or isotopes of an element possess nuclear spin? We can answer this question. But remember, there is an empirical rule to predict NMR activity of a nuclear spin. That means I can find out whether a given isotope of an element, whether that particular nucleus has a spin or not. Look at this table which is given here. In the top row, you have atomic mass, atomic number, and few examples of nuclei, total nuclear spin, and last column tells me whether such nuclei are NMR active or not. If you go to the second row of this table, you will see you can come across some nuclei whose atomic mass is odd number and whose atomic number could be either odd or even, does not matter. For example, take proton, hydrogen atom. In NMR jargon, we call it as a proton. Henceforth, if I say proton, do not get confused with the proton of the nucleus. It is nothing but a hydrogen atom. It is a convention used in NMR spectroscopy. And next you see the carbon 13, nitrogen 15, phosphorus 31. All of them have atomic mass as odd number. And such nuclei will have what is called spin half nuclei. They are called spin half nuclei. That means they have spins equal to half integer here. Okay, spins are half integer, half 3 by 2, etc. And last column is very important to see such nuclei are NMR active. All spin half nuclei are NMR active. Go to the next row where atomic mass is even, atomic number is odd number. An example, for example, we have nitrogen 14. Also examples of deuterium and boron 10. These have integer spins like 1, 3, etc. Such nuclei are also NMR active. Now go to the last row. Atomic mass is even number. Atomic number is also an even. Examples like carbon 12, oxygen 16, S32. You can see carbon 12 atomic mass is even, atomic number is also even. Such nuclei has nuclear spin 0. That means such nuclei, if you look at the last column, tells me they are not NMR active. They are called NMR silent nuclei. You cannot study NMR of such nuclei. Now we have, I said, half integer spins and spin 0. Let us see spin half nuclei. Spin half nuclei have a charge distribution which is spherical in shape, and their behavior is easy to understand, and we call such spin half nuclei as a dipole, as if it has two poles of a magnet. It can be treated like a tiny magnet. So they are called dipoles. And if you consider nuclei with spin greater than half like this, they have non-spherical charge distribution. Look at this one. Here negative, negative and positive, positive. There are 4 charges, quadrupole. These are 4 poles are there. And such type of, this is non-spherical. So such type of nuclei, they are called quadrupolar nuclei, and they possess electric quadrupole moment. And their behavior is slightly difficult to understand compared to spin half nuclei. Okay. Now with this, let me introduce to you something about what is called a spin quantum number and a magnetic quantum number. This is a very important concept. You require to understand this to know the concept of NMR. For example, if I have to consider any nucleus, there are 2 quantum numbers associated with spin angular momentum of the nucleus. Nucleus spin angular momentum has 2 quantum numbers. One is spin quantum number I, other is magnetic quantum number F. This magnetic quantum number has constant magnitude and direction. These 2 are very important, and these 2 quantum numbers will determine the properties of the nucleus. If you take any nucleus, these 2 quantum numbers are enough to define or to understand the properties of the nucleus. Okay. Now we can also talk about the magnitude of this nucleus spin angular momentum, which is given by spin quantum number I. The angular momentum, if I consider its magnitude, is given by, in terms of I, spin quantum number, by a simple equation which is P is equal to h cross root of I into I plus 1. Don't worry about how we derive everything. It is just an equation I am giving you. Please take it. What is h? Of course, we all know h is a Planck's constant, which is divided h divided by 2 pi. H cross is equal to h divided by 2 pi. Now the z component of the spin angular momentum is quantized in a given magnetic field. It is always quantized. You all know in quantum mechanics, quantization, etc. So z component of the spin angular momentum P is given as Pz is equal to m into h cross. Okay. What is m now? M is called the magnetic quantum number. Okay. M is a magnetic quantum number which is related to spin angular momentum, z component of the spin angular momentum. Now the magnetic quantum number m in turn depends on what is called spin quantum number I. I told you about spin quantum number and I told you about m. They are all related to spin angular momentum P. Now the magnetic quantum number m is related to I, and it takes the values from minus I to plus I in steps of 1. For example, if I take I is equal to 0, y equal to 1, it starts from minus 1, add 1 0, add 1, it will become plus 1. So that means it has 2i plus 1 possible orientations. For example, I consider nucleus spin half nuclei. That is what we are going to deal with most of the time. As I said, there are 2 possible orientations because it takes the value from minus I to plus I. If I is equal to half, it is minus half, then add 1 for it, it will become plus half. So that means spin half nuclei have only 2 possible orientations, okay. And go to the spin 1 nuclei. There are 3 orientations. I is equal to 1, start with minus I, that is minus 1, 0 and plus 1. If you go to 3 by 2 nuclei, spin 3 by 2, there are 4 possible orientations, which is given by minus 3 by 2, minus half, plus half and plus 3 by 2. Start with minus I, I is equal to 3 by 2, minus I minus 3 by 2 plus add 1 becomes minus half, add 1 becomes plus half, add 1 more becomes 3 by 2. So, for spin 3 by 2, there are 4 possible orientations. Like this you can work out for the spin of any given nuclei what are the possible orientations, okay. The quantization direction of the magnetic quantum number, especially for m is equal to I, which for mi is equal to half. Now there are 2 possible orientations I said for mi, which is m is equal to half. When it is plus half, the spin angular momentum orients in the direction of the field. When mi equal to minus half, it orients opposite to the direction of the field. There are 2 possible orientations. This is the magnetic field. For m is equal to plus half, the orientation is like this. M is equal to minus half, the orientation is like this. And there are only 2 possible orientations. For of course, m is equal to, for I equal to 1, we have 3 orientations. Then we have 1 like this, 1 like this, 1 like this. There are 3 possible orientations. So like this, we can work out the quantization directions for any magnetic quantum number mi. And for the mi, as I said, there are only 2 orientations. One is called plus half, other is called minus half. In NMR jargon, we call it spin up state and other is spin down state. Plus half is spin up state and minus half is spin down state. Conventionally, spin up state is called alpha state and spin down state is called beta state. Remember, when I am talking in future, when I am analyzing the spectra etc., if I say alpha state and beta states, you should immediately understand when I say alpha state it is a spin up state, beta state is a spin down state. These are the 2 possible orientations for spin half. And of course, we can get the magnitude of the spin angular momentum in each of these orientation directions. For example, this is the, we know mz which is equal to m of h cross, I told you already, and I know p is equal to this thing. Simply use the trigonometry rule and you can find out what is this. It's very easy to calculate this thing. So I am not going to the details of that because it has already been discussed in couple of 2 of the earlier courses. Now we will go into what is called the nuclear magnetic moment. Mu, it is a vector again, this is a very important term. This is what is very important in understanding NMR spectroscopy. Okay. Let us start understanding charged nucleus, which is undergoing rotation with an angular velocity or angular frequency omega, which is given by 2 pi nu. It creates a magnetic field that is called B or B naught, what you call. And it is like this, the spin is rotating like this, whether it is clockwise, anti-clockwise does not matter. You can treat it like a small tiny bar magnet because it generates a magnetic field, and we call it as one is the north pole and another is the south pole here, and that is why we call it as a dipole. This is applicable only for spin half nuclei. For of course spin greater than half, I told you it is a quadrupolar spin. We have 4 poles, so it cannot be treated like a dipole. Okay. So I can say if I am dealing with a spin half nucleus, I can treat the nuclear spin like a tiny magnet. Okay. So with this, when I say nuclear spin, I can treat like a tiny magnet. You all know in your school days, when I say it is a magnet, I can define a magnetic moment. So nuclear spin, since I can treat it like a tiny magnet, it has a magnetic moment mu, also called dipole moment. It has a magnetic moment mu, and mu is a vector. I can easily understand mu in the vectorial representation. So if I consider magnetic moment mu, also it is proportional to spin angular momentum P, which is given by a simple equation mu is equal to gamma into P. It is a simple expression. What is gamma here? Gamma is called a gyromagnetic ratio, and interestingly it is constant for a given nucleus. If I take the hydrogen atom or proton nucleus, it has one gamma. Go to carbon 13, nitrogen 15, different nuclei, they have different gamma. But for a given nucleus, that gamma is a constant. Alright. So now I substitute this P in mu. I knew what is P. Already I have written already, P. P is equal to h cross into root of I into I plus 1. Earlier I wrote. Now mu is this equation. Now I put I is equal to 0 here. What will happen? Then mu becomes 0. That means no magnetic moment. So that means if nucleus has no spin, it has no magnetic moment. Since magnetic moment is very important, as I go ahead further I will tell you, in understanding the concept of NMR, interaction of the magnetic moment with the external magnetic field is a criterion to see NMR spectroscopy. If mu is 0, no NMR. That means if I is 0, no magnetic moment. When there is no magnetic moment, there is no NMR spectroscopy. That is the reason why in the table I told you, for the nucleus with even atomic number and even atomic mass, I was 0, and I said such nuclei are NMR silent nuclei. That is what it is. Because of this, they have no magnetic moment and they cannot interact with the external magnetic field. Now if I come to the gamma, gamma value is constant for a given nucleus, and different nuclei have different gamma, and it is a simple SI unit. It is given by gamma is given by some number into Tesla per radian, for some value it is given, and it is radians per second per Tesla. Okay. For example, if you take proton has a value 26.753 into 10 to the power of 7 radians per Tesla per second. If you go to the carbon 13, gamma is nearly 4 times smaller. Instead of 26, it is 6.728 into the 10 to the power of 7 radians per Tesla per second. Okay. So with this, we will now try to understand how the nuclear magnetic moment interact. Okay. How the interaction of different nuclei is taking place in the magnetic field, or in other words, how the magnetic moments do interact in an external magnetic field. This concept is very, very important. And before that, I want to tell you what is a gyromagnetic ratio. I said it is a constant for any given nucleus. Fine. This can be also worked out, and gamma is given by a simple equation, which is gamma is equal to e to the power E over 2 into mc. E is the charge and m is the mass. Of course, E is the velocity of light, we know. Nuclei with higher mass have lower gamma. Look at this, mass is in the denominator. That means as you go to higher and higher, heavier isotopes, gamma becomes smaller and smaller. That means if you understand that, among all the stable isotopes of all the elements of the periodic table, proton has the lowest mass and has highest gyromagnetic ratio. That is the important concept. Remember, all the NMR active nuclei, if you consider, the one which has the highest gyromagnetic ratio is proton compared to any other nuclei. So now the question is, we will understand what is the difference between proton and carbon 13. Both are spin off nuclei, that is spin quantum number is a half, then magnetic quantum number is minus half and plus half. Then what is the difference? Both are same. The difference comes in gamma. If you look at gamma, gamma is equal to E over 2 to the power of mc. Now m is different. As a consequence, what happens? Mu is different. Gamma is different, so mu is different. So mu is equal to gamma into P. So although both proton and carbon 13 have the same quantum spin quantum number I, same magnetic moment I, magnetic quantum number m, their magnetic moment I is different. These two have different magnetic moments. That is why different nuclei have different magnetic moments and they can individually studied. So, all nuclei with different gyromagnetic ratio can be individually studied. That is the beauty, because if you go to the periodic table, there are so many elements in the periodic table. Many of them or all of them are at least one isotope of each of the element is NMR active. That means every element of the periodic table can be individually studied by NMR. Okay, these are the characteristic properties of some selected nuclei. I have given here most important. Look at the proton and its abundance and spin and finally gamma. This is the one which has the highest gamma. As you keep going down here, you can see different natural abundance is there, spins are different, and then magnetic moments are different. And this is just for the information. So, commonly investigated nuclei in chemistry and biology are proton, carbon, nitrogen, phosphorus and fluorine. All of them are interestingly spin half nucleus. Very easy for us to understand. They are spin half nuclei, easy to understand. Whereas, if you want to study, go to inorganic chemistry or material science, we study boron, aluminum, O17, etc. They are all spin greater than half. Of course, silicon is S29, Si29 spin half, but other nuclei have spin greater than half. So, these are all the things. With this, and now the time is up, what I am going to do is this general introduction with what I have given today just now. We will stop here. Next time next class I am going to discuss about Zeeman interaction. Basically what I try to tell today is I introduce the concept of the spin quantum number, magnetic quantum number, possible orientations of the magnetic, the quantization directions for different Mi, for different M, which depends upon spin quantum number I. For example, spin I is equal to half. We have two possible orientations. One is plus half and minus half. Plus half orients in the direction of the field and minus half orients in the direction opposite to the field. Okay. And then different nuclei has a different gamma. As a consequence, there are different magnetic moments. So, they can be individually studied. This gamma has a particular unit which is radians per Tesla per second. Then different nuclei has different gamma. Although I is same, M is same for different nuclei, but gamma makes them different. As a consequence, different nuclei can be individually studied. So, with this I am going to stop here. We will come back and continue in the next class. Thank you very much.